ZOD is a pretty cool TypeScript validation library, and the really neat thing about ZOD is that it gives you type safety both at compile time, which is where you usually have it with TypeScript, but also at runtime, where you don't usually have it with TypeScript. And we're going to take a look at how this works today. Now, we're not going to use the ZOD library. Instead, we're going to build our own very small version of what ZOD does so we can get an idea for how that works with TypeScript behind the scenes. So let's start by taking a look at ZOD and kind of how this works. I'm here at zod.dev, and we're going to take a look at the basic usage example. We can create a schema by using Z or Z dot and then some data type like string. Now each schema has a parse method on it, and if we pass it a string, we'll get back that same string and we'll have validated that that is properly matching the schema that we created, in this case a string. Now notice down here, if we pass parse the number 12, this is actually going to throw an error because the value that we pass it doesn't pass the validation. And of course, we can do more complex things here. We can create these objects, maybe an object with a username that's a string, and we can parse that type. And the really neat thing here, of course, is you're getting a runtime validation. This object or value does match whatever schema I'm setting up, but you also have compile time checking so that we can actually now use that value as a strongly typed value. So let's take a look at how we can build some version of this in TypeScript. Of course, what we're going to do is just a small sliver of what ZOD can do. Obviously, use ZOD in your projects. Don't write this yourself. But if you're curious about how this works behind the scenes, this is one way that you could do it. It really all comes down to this syntax right here. Asserts val. For starters, let's look at these two functions here, which are asserting some primitive JavaScript types. We've got strings and we've got numbers. Both of these functions take some value that is of an unknown type. This is the set of all possible TypeScript values. Who knows what it is? And then inside of these functions, we're going to check to see if this value is a particular type. In the case of isString, of course, we're going to check to see if it's a string. In the case of isNumber, we'll check to see if it's a number. Now, you'll notice that in both of these cases, we're actually negating these checks. So we're saying, is this not a string or is this not a number? And in the case where the value for this first one here is not a string, we're going to throw an error here. And we have a little error helper utility here. And so we're going to throw an error saying this value is not a string. In the case of isNumber, of course, if val is not a number, we're going to throw something saying that this value is not a number. And that's all we do in these functions. We don't return anything. We just throw an error if it's not the type we want. So this uses the typical style of an assert function, or maybe an invariant function. We pass some value that we're going to perform some check on. Often assert functions just check to see if a value is truthy or not. In our case, we're actually checking to see if it is of whatever type we expect. And if it doesn't pass the check, we throw an error. Now, the way this works with TypeScript is when we define the return type here to say asserts val here being the name of the argument we're checking, is type. So asserts val is string or asserts val is number. What happens is after we call this function, TypeScript now knows the variable or the value that was passed into this function is whatever type that we say this function asserts for if the function doesn't throw an error. So let's take a look at how this might work. Const u, some unknown value that is a string. And then what we could do here is say is string u. Underneath that call, let's check what the value of u is. You can see it's a string. Up here, the value is unknown. We pass it to isString. And then down here, we know the value is now a string. What's happening here is TypeScript knows, based on our return type, that if this is not a string, then we will have thrown an error and we're never actually going to reach line 16 here. We could actually change this to isNumber, and we're going to see a similar thing where up here, of course, u is still unknown. Down here, u is a number. Now we know, because we're looking at this code right now, that u is not a number, it's a string. So how could u ever be a number? Well, what we know is that isNumber is actually going to throw an error. Now this example also shows us that we do need to be pretty careful with this type of logic. TypeScript is casting u to a number here based solely on the information that we give it. This is one of those places where we're going around the type system and saying, this is the type of a particular variable instead of letting TypeScript figure that out for us. Now, of course, we are using an approach that TypeScript itself will understand. TypeScript does know what type of means in our case. For example, if we add an else block to this if statement and look at our value, val is a number. TypeScript understands how type of works. However, that's kind of incidental in this case. The fact that we're using type of here has nothing to do with the fact that our assert is working. For example, maybe instead we could just do absolutely nothing in this function. So it doesn't throw an error. It doesn't do any type checking either. But what's happening now is u is still being cast to a number because we've told TypeScript we trust the implementation of his number. So if you're going to use asserts in this way, you got to be pretty sure that you've got the right logic in there to actually prove that your value is of whatever type you say it is. But once we have these functions that we trust, we can now do some interesting stuff with them. So let's build up our own version of ZOD here. I've got a couple of types just to show us what's going on. We've got this assert function. I'm not actually using this type anywhere, but this is going to be the type of any of these assert functions like isString, isNumber. This just takes some unknown argument and it asserts that this argument is whatever type this assert function is for. Now a parse function here takes some argument of unknown type and it returns a value of t. Now we know based on the way we're going to use this library that the value of t that is returned is going to be this argument. And what's happening here is each parse function will use an assert function to check that this arg is of type t, and if it is, it will return it. And of course, if it's not, we know the assert function will throw an error. And finally, we have our parser here, which is simply an object that has a parse function on it that parses to a particular type. So how can we start building these validators? Let's look at these first two in our constant x here. And of course, we have string and number here. And these represent our basic primitive validators that we've already built. These return objects that have parse functions on them. They both take an unknown argument. Parse on string returns a string. Parse on number returns a number. And as you can see, the implementations are pretty straightforward. We validate that the argument is the type we expect it to be. And then in our return statement here, you can see arg is a string. And down here, you can see arg is a number. And we can take a look at how these work down here. We can create a string parser here simply by calling x.string or x.number. Those return our parsers. String.parse, pass it, in this case, a number, and the value we get out is going to be a string, or it's going to throw an error. So validations for primitive types like that are pretty simple, but let's look at some deeper objects, because this is where things I think get kind of interesting. So we know we need to follow the same structure. We need something that asserts our object is the shape that we want it to be, and then we can just return the object that we were passed in. But how are we going to assert the type of a possibly deeply nested object? So we have this object function here. We've got a couple of generic parameters that will be inferred. We don't have to define these, mainly just some type t. And then we have s, which is our schema, and s is going to extend a record where we've got string keys and then parser of t's as the values. It's going to look something like this right here. So we're going to call x.object, and then we can pass it our keys with other parsers as the values. So we can have a name that we expect to be a string. We can have an age that we expect to be a number. Because x.object is a parser, we can actually deeply nest this here. And as you can see in our example, we've got a deeply nested props here, where at the bottom we expect a string, but we have x.object, x.object, x.string to bring us all the way down. So how do we write an implementation for x.object? And of course, remember, there's two parts to this. First is we have to write the code that actually does the runtime checks to validate that this value that we get at runtime is the shape we are asking for. But the second thing we want to do is at compile time, or at development time for us when we're working in the editor, we want TypeScript to know that if this validation passes, then this is a strongly typed shape that matches the shape we're describing. So we want to have both the compile time and the runtime support here. Here's how this works. We return our parse function. We take that unknown argument, we're going to validate it, and then return it. Really, all the work happens in this validate function. So that is a function that we just have inline right here. So of course, let's start at the top. We've got a function validate that takes some unknown argument. And then of course, we need to say that we assert that the arg is some type. And in this case, we're just inlining this object type right here. What we're going to do is actually create a mapped type here, where we're mapping over the keys of s. And s, of course, is the type of our schema here. So whatever schema we pass in, we're going to map over the keys of s. So for each key of s, we're going to call those keys k. We're then going to map into s with that k. So we're at s.k.parse. S here is going to be the type of this whole object. K, for example, will be name or age or deeply. And then the value for that, of course, is x.string. X.string is its own parser type here. So when we say s.k, k could be name, for example. So this is the same thing as saying our schema.name.parse. And so we're going to get that parse function, and then we're going to use the built-in utility type return type, which takes some function as a generic parameter, and we're going to figure out what is the return type of the particular function that we're looking at right here. And of course, we know that for this function right here, the return type is a string. And so when k is name, this value is going to be string. And so you can see how as we go through each key, we're going to get that strongly typed object out of this. And all of this, of course, is part of our asserts. So we're asserting that the arg matches the same type that the schema represents. So that is the compile time piece checked off. This validate function now asserts that the argument matches a particular TypeScript type. And so now, of course, when we do this validate down here, our arg is going to match that type. If we hover over arg down here on the return, you can see that arg will match whatever type comes out of the schema that we give it. Compile time check complete. Let's talk about the runtime check. So because arg is unknown, there are a couple of checks that we need to do first to make sure that it is actually an object that we can start looking at the keys of. First, we need to just check, is this a truthy value? Then we want to check that it is actually an object. Finally, we check to see if it's an array, because an array is an object. And so if this is an array, we also don't want to match, so we throw an error. After we get past these three guards, we know that arg is an object. In fact, if we look at the type of arg here, I can hover over it, you can see all that we know is arg is some kind of object, but that's enough for us to work on here. So now we're going to do object.keys on our schema. So we're going to start looping over each key in the schema. And as you can see, for each key, we're going to check to see if that key is in argument. Now, unfortunately, because k is just some string, there's no way for TypeScript to know that arg now has some property k on it. If k was actually a hard-coded string here, say foo, then what we would be able to tell here, as you can see if I hover over arg, that we know arg is some object, and at the very least, it has a property foo on it. Unfortunately, we can't do that with k here, which means that when we actually want to index into the arg here, we've got to do some other explicit typecasting, which I'm not a fan of, but it's kind of unavoidable. So we have to cast arg to any so that we can then actually index into k. But we'll still do this check anyway, because if there is no property k, then we know that this object can't actually match the type that we want. And so in our else block here, we'll throw an error. However, if arg does have a property k, then we want to use the correct schema validation function to validate that property k. And so we can say schema at k dot parse, because schema at k is a parser, and then we're going to pass in that value. And this right here is kind of where the recursion piece happens, right? You might be wondering, how do we get this deeply nested props thing here? And the nice thing is that in the case of deeply, we're passing the full object in whatever value that we're validating. We pass that object to this nested parser here. By just basically delegating to each of the key parsers, we don't really have to think about recursion too much ourselves. What's really nice here is the same thing is kind of happening at our type level here, because if k is, in our example, deeply, or some key that has an object parser, then we're just going to get the return type of that object parser, which is basically going to loop inside of object once again with the sub parser, if you will, for that particular key and find the type for that. So that's really all that we need to do. We throw errors in all of the cases where we find that this thing doesn't match. And of course, if schema.parse doesn't match, then that will throw an error of its own and we'll exit this function. If it doesn't throw an error, then we're going to check our next key and we'll be on our way. And so with all of that in place, you can see we've got our object parser set up here. One of the nice things about this strong typing is that if we hover over object parser, you can see object parser takes some unknown argument and it returns the exact shape that we want. Name is a string, age is a number, deeply nested props is a string. And finally, we can actually use it. We'll pass it an empty object here just to have some value in there. If we hover over value 3, we can see name is a string, age is a number, deeply nested props, where props is a string. So that's an example of how the ZOD library kind of works behind the scenes. Of course, ZOD is much more complex. Definitely don't write your own implementation of this, use ZOD. But I think it's fascinating to learn about the underlying behaviors in TypeScript that allow awesome libraries like ZOD to exist. So if you have other TypeScript libraries that you use and you wonder, how do these work? Definitely leave their name in the comment below, and maybe we'll check them out in future videos. Thank you so much for watching, and I'll see you in the next one.